This thermometer is 1 degree. This thermometer has a plus 1 degree Celsius error, which means every temperature it measures is 1 degree Celsius more than what it is. So now you have to read the question very carefully. Have a look. What is this question asking? The increase in temperature. What does this tell you? Does it mean an exact temperature or does it mean the difference in temperature?
Difference.
Difference.
So what do you think? What should the difference be? Is it going to be correct or is it going to be same?
Correct.
The difference is going to be correct, but the actual temperature measurement is not going to be correct. Actual temperature measurement is going to be 1 degree Celsius too high, but the difference in increase in temperature is going to be correct. So for this MCQ, this is the correct response. If the question asked, the temperature of the water calculated from her results is, if they didn't use the word temp increase, then this answer should be 1 degree Celsius too high. বুঝে গেছে আমি দুটো অ্যাসপেক্ট আলাপ করলাম Is it clear? No, it is not.
G sir, clear.
আচ্ছা আরেকটা কোশ্চেন কোনটা বলছিল সিমিলার একটা কোশ্চেন বলছিল যেটা এটা এই যে this is the question. This is a similar question, but this is different than the other one. A thermometer reads 1 degree Celsius in pure melting ice and 101 degrees in steam above boiling water. It is used to measure the temperature of water before and after it is heated. What is the error when the temperature rise is calculated? So temperature rise also means temperature difference. Temperature rise means final temperature minus initial temperature. So this would be zero error because the whole scale is 1 degree shifted towards positive or positive error, which means that every measurement is 1 degree Celsius more high. So if you do the difference, you're gonna cross off those things from the same thing. So this one would also be zero. তারপর
স্যার আমি না ডিসকানেক্ট হয়ে গেছিলাম 17টা একটু আরেকবার বলবেন
this is the word. This word. Highlight on this word. Let me show you. It's too big. Right. Emphasize on this word. Nothing.
ওকে স্যার আই গট ইট
তারপর 20.23 anyone?
Sir, 15.2 থেকে 5 and 8.
5 in it. So 15.25. Let's have a look for 5. A certain liquid is used in a liquid in glass thermometer. It does not expand uniformly with temperature. It does not expand uniformly with temperature, so it doesn't have linearity. Okay. What if it would this have on the scale of the thermometer? It would be non-linear. That's all you can say. Non-linear means if we actually make a liquid in glass thermometer like that, let's say this is the liquid in glass thermometer. Here is the bulb and here is the bore that goes in like that. And here is the bulb plus bulb. Typical thermometer which has linear expansivity has equal temperature grading on a for equal length. For example, let's say maybe for 1 centimeter you're going to have 10 degrees Celsius, and so every centimeter is going to represent 10 degrees Celsius all the way up to the highest point, highest reading that this temperature is capable to measure. But if it is non-linear, it means your gap, physical gap in terms of length for equal temperatures over the entire range of the scale is not going to be same. In some cases it's going to be more, in some cases it's going to be less. To give you a better idea for the meaning of the term non-linearity, let me just show you this thing. What this one represents that the length of the liquid column increases the length of the liquid column with respect to temperature. So let me just write delta L by delta theta because that's the two factors. This is not going to be straight line. This is going to be, let's say, a curve. So if you try to observe equal amount of delta theta for multiple two spaces, for example, let's say if you consider this much delta theta for the initial space, you have a delta L of this much. If you consider the same amount of temperature change over here, you have a delta L of how much? One intercept over here, the other intercept over here. So you can see it over here very well. For equal amount of temperature change, you are having different amount of delta L's, right? This is the basic significance of the term nonlinearity, which means if we try to plot, if we actually graduate or calibrate this thermometer using this liquid, which is built up with this liquid, at lower temperatures, at lower temperature, a small length would represent a pretty large amount of, for example, let's say a small length represents 10 degrees Celsius. As the temperature goes higher, you're going to need bigger and bigger length. Do you understand what is happening here?
Yes, sir.
বুঝে
This
গেছে
is
কি জিনিসটা আবার?
non-linear liquid light, right?
Sorry?
Sir, this is non-linear, right?
Exactly. So this didn't necessarily need it to be increasing gradient. I could have also drawn a decreasing gradient. If it was drawn as decreasing gradient, you're going to have larger gap in the beginning and lesser gap on the later. But truth be told, this will not have equal gaps for equal temperature. That's the whole information. বুঝতে পারছি?
জি স্যার।
Good. তারপর 8. Let's look at number 8. The sensitivity of a liquid in glass thermometer depends on the volume of liquid used and the diameter of the bore of the thermometer. Which changes will produce the greatest increase in sensitivity? Beautiful question. Let's take it out. Okay, we are already given 2 hints. The sensitivity of a liquid in glass thermometer depends on the volume of a liquid used and the diameter of the bore of the diameter. Which changes will produce the greatest increase in sensitivity? Try to understand. Volume of the liquid affects the sensitivity in terms of more, less. I mean, if you have a smaller bulb, you're going to have less sensitivity compared to if you have a larger bulb, you're going to have a bigger sensitivity because more volume of liquid will expand more. Then for the bore diameter, come to think about it, if you have equal volume increase for 2 thermometers, a thinner bore will give you a longer height covered for the same volume. A thicker bore is going to give you a smaller height coverage. So if you want to have increased sensitivity, you need to cover longer length, which means you need a thin bore and a large bulb. These 2 factors will give you more sensitivity. Is this understandable?
Yes, sir.
So which one do you think is the correct response?
C.
C is the correct response. Yeah.
Sir, could you explain the bore diameter one again?
Yes. If you consider, like I said in the earlier class, that whenever we're considering one characteristics, we should try to visualize 2 thermometers placed side by side, which are identical in all of their aspects, except for one variable. So try to visualize 2 thermometers placed side by side, where one thermometer has a smaller cross section of the bore, another thermometer has a larger cross section of the bore. Try to think about it. If both the bulb has everything same, bulb size same, liquid same, material same, bulb wall thickness same, everything else is same. Now think about it. If you increase the temperature by equal amount for both of these thermometers, the actual volume increase of the liquid, thermometric liquid, delta V, will be equal for both of them. But the one that has a thinner bore, your pi r square h, r is too small, so h would be large. But the one that has a bigger diameter or bigger radius, your pi r square h cylindrical volume, here r is large, so h has to be small. Right? The same volume. They both represent the same delta V. But this one covers a longer height, this one covers a smaller height. Now, what do you need for high sensitivity? Which one do you need to achieve higher sensitivity?
Smaller bore.
Smaller bore. So that's why bore diameter should be decreases. So C is the correct response for this question. বুঝছো?
জি স্যার।
Beautiful. What else? And 9? Oh, that's it. Beautiful. আচ্ছা, তাইলে তো এটা গেল। তোমাদেরকে আমি একটা জিনিস পড়াই নাই, জিনিসটা আমি এখন তোমাদেরকে পড়াবো, সেটা হচ্ছে what is the purpose of constriction in clinical thermometers? আমার কাছে ফেডারেলের বইটা নাই। Can someone pull up, all of you who you have the federal book, please pull up the table where you have the properties listed in your book for the federal book, and tell me the page number. Someone. Clinical thermometer যে পেজে আছে। There is a sky blue table.
Page 124.
Page 124, according to one of your friends. Please turn that up and have a look. Oh, Ibtisam, by the way, Mashrafi told me about your requirement and I'm working on it. I'll let you know personally once that's done. Okay.
Okay.
Beautiful. So in page number 124, you can see the construction of a clinical thermometer. There is one additional thing than laboratory thermometer, which is a constriction. You can see that there's a very kink kind of thing, or there's a very ঢেউ খেলানো type of the curved, smaller diameter part of thing between the actual bore and the bulb of the thermometer. So what's the purpose of this thing? This is what we call constriction. So to represent, to explain that thing, let me just pull that up. So we could actually use this or this one. All of them can be used. Bum, 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 bum. Okay, the longer we go, the poorer the figure becomes. So let's just take this one, copy the image. If we paste it over here, how it's gonna look like? It looks like that. Okay, open image in new tab. Screenshot. Screenshots are always helpful. Boom. All right. So let me explain the purpose of this clinical thermometer. One of the things that you need to understand that clinical thermometer is used to measure the temperature of human beings. Preferably, there can be other thermometers which are used for veterinary purposes, like to measure the temperature of cats and dogs and other animals. That can have other properties, but for human beings, we are warm-blooded animals, which means our internal temperature, our core temperature, is constant. For our physiological systems to work, we need to maintain a certain temperature within our body. If the temperature drops significantly below that level, many of our physiological operations, chemical reactions, sensitivity, nerve connections, heartbeat, many of these operations can be disrupted. That's what I mean by saying that we are warm-blooded animals. So the temperature of human being is about 98.4 degree Fahrenheit for a healthy human being. Fahrenheit is a scale which is a much bigger number of division within the ice point and the steam point. So that gives us a bit more precise understanding. So that's why for human temperature sometimes Fahrenheit is still used. Although you don't need to know, but let me just tell you that degree Celsius scale has 100 divisions between 0 degrees Celsius and 100 degrees Celsius, whereas Fahrenheit scale has 180 divisions between ice point and steam point. I'm not saying it's 0 and 180. It is actually something else. So it is 32 and 212. So why 32? I'm not getting into that. It's a bit of a history, so I'm not covering that. But I'm telling you that the Fahrenheit scale has 180 divisions between ice point and steam point. So gives us a bit more sensitivity by default because of the scale has more divisions in it. So that's why sometimes it is used. If we convert that 90.4 degree Fahrenheit into actual degree Celsius scale, we get 37.6 degrees Celsius or about 37 degrees Celsius, 37.4 or 37.2, I think. I forgot, but somewhere close to 37. So 37 degrees Celsius can be considered to be the actual core temperature of a human being, healthy, regular human being. If the temperature of human being drops by 2 degrees of Celsius, that person will have hypothermia and move towards death. If the temperature goes much higher by, let's say, 4 to 5 degrees in terms of Celsius, that person is going to also get closer to death. So to measure the temperature of a human being, we don't need to have a very large range. Our practical requirement for the thermometer can be limited from 35 degrees Celsius all the way up to 42 degrees Celsius, as you can see in this figure. Because any person who has a core temperature lower than 35 degrees Celsius, 35 degrees Celsius is dead. Any human being who has a core temperature more than 42 degrees Celsius is also dead. We are not interested in dead people. We're interested in alive people. So that's why clinical thermometer has a very small and precise and well-defined range, which is useful for us. Now, this is the basic description of the clinical thermometer, the difference for the clinical thermometer between one of the differences of the clinical thermometer with the laboratory thermometer, typical laboratory thermometer. Why do you need the constriction? Now, try to understand this thing. If the constriction did not exist, what would have happened? Let's try to understand that. One other thing, can all of you know how to see the temperature from our clinical thermometer that you have at your home? I mean, you don't actually see it. You have to tilt it a little bit and see the shiny mercury, and that's how you read the temperature. Do all of you know how to see a thermometer? Everyone?
Yes, sir.
No, sir.
Okay.
Yes.
For those of you who don't know it, learn it from your parents tonight. If your parents are not available, grab one of your senior person, bribe them, whatever they want, learn it. Learning two things is very important. Learning how does an analog clock tells time, and also how does a analog thermometer, not digital thermometer, gives you temperature. You should know these two things pretty much like you should know swimming. I don't know swimming, so that's wrong on my part, shortcoming on my part, but you get my point. So the reason I'm bringing up this idea of that how the thermometer has to be seen is that you cannot simply hold the thermometer in your hand and be able to tell the temperature. You have to hold it in your hand, tilt it a little bit against the light, and at one point the mercury surface is going to start reflecting because of its shiny silver color, and from that reflection you'll be able to tell what the temperature is, because only at that position your eye is at perpendicular or nearly perpendicular to the surface of the mercury. So it is a very thin rectangular capillary tube. So the thickness of that rectangular hole is very thin, so that we have a very high sensitivity. Yet the width of that bore is actually quite wide, so that we can visibly see the thickness of the mercury, and by means of reflection of light. And to further help the process of viewing this thing, if I just show you the cross section of this thermometer seen from the side, it has a bit of a pear-shaped shape. Pear, P-E-R, pear. What's the pronunciation of P-A-R? PR or pear?
Yes,
What's the pronunciation of this?
that's fair as well.
Okay, I'm gonna look it up in Google and pausing recording because I'm dumb. So we're resuming the recording. We just looked up the pronunciation of pear and pear. Anyway, the shape of this thermometer, if you've seen from the side, the cross-sectional area of the thermometer has a bit of a shape like this. It somewhat looks like this, and it is intentionally designed in this way. The thing that I was telling you, now I'm going to try to draw that bore and figure not down to scale, or I could actually try to draw it in scale by superbly zooming it in. So the mercury bore might as well be this much thick with this much wide inside. I need to put a bit of a gap in between. This is how the mercury bore looks like inside the thing. And this curved shape actually helps to magnify this whole thing, because that's how lenses work. So the reflection can be seen. I mean, all this is very small. This is going to look like they're very wide because of the magnification factor. So that's how it looks like. So that also helps for better visibility and easier to read out. So why do we need the constriction? The purpose of the constriction is to break the continuum of the mercury, liquid mercury, whenever the temperature of the bulb starts to drop. Let me explain. Before we take the temperature of a human being, we actually shake the thermometer a little bit, holding it somewhere over here, so that if there were any mercury within this bore from earlier measurement or for room temperature, this is going to go all the way down, and it's going to go all the way to the bulb. We need to make sure that this bore is absolutely or almost pretty much empty. I'm sorry. Yes, done. So we need to make sure that this thermometer is actually, the bore of this thermometer is actually quite empty uh, for this to work out. And then we're going to put this thermometer into the patient's body, either in the mouth or in other places to make the temperature. And we're going to wait for a while, within which time the heat from the patient's body should enter into the penetrate through the glass wall, bulb glass wall, and eventually this mercury is going to expand and push the mercury through the small constriction and eventually into the bore. And this level is going to slowly go further to the right, and eventually it could get set at a level which represents the actual core temperature of the patient. This is the important bit. Now, to observe the temperature, what are we going to do? We have to take this thermometer out of the patient's body, and we have to do the trial and error of tilting, and then we can take the temperature of the patient. This is the thing. Whenever we are going to put the thermometer out of the patient's body, this bulb is now going to become in contact with what? Atmosphere. Logically, the atmosphere is cooler, or the atmosphere is cooler. Typically, the atmosphere is cooler compared to the temperature of the patient. So whenever this within the time that the doctor takes out the thermometer out of the within the time the doctor takes out the within the time the doctor takes out the thermometer from the patient's body, and it tries to see, let's say 5-6 seconds passes by within this time duration. Within that time, it is possible this marker is gonna contract, and if the constitution doesn't exist, if the constitution doesn't exist over here, this mercury is going to pull back this mercury over here because of what we call metallic bond. Metals try to do what? Maintain their unity together. Do you know how metallic bond works, one?
Yes,
Yes.
sir.
So whenever if the mercury within this bulb actually starts to contract, this is going to try to pull that mercury within the bore towards left. So if this constitution does not exist, and if we have a continuous bore like that, by the time the doctor is actually able to take the reading, it is possible that the temperature seen over here might be a couple of fraction of degrees less than what the actual temperature is, which is going to be a wrong information. We want to measure the temperature of the patient exactly and precisely, and that's where the constitution comes in and help us. Let me show you how it happens. Whenever the mercury expands, when the thermometer is placed inside the patient's body, the thermometer expands and it simply pushes out through this small channel and eventually fills up the whole bore. You have to understand this, but the glass wall in the bore is actually quite thick, where the glass wall in the bulb is actually quite thin. So heat dissipation from here is pretty easy compared to heat dissipation from here. This is actually pretty difficult because it is a very thick wall. You can see that how much of a glass over here, whereas the bulb might actually look like a very thin glass wall, like super thin, this kind of thing, because we want to achieve good conduction, good transfer of heat energy to the bulb. Hold on just a second. I had to pick one of my parents' call. It was due 1 week back, so before I set your routine. আচ্ছা, anyway, কি বলতেছিলাম? Whenever this mercury is going to start contracting, this is going to try to pull it back. So because the constitution exists over here, as the mercury of this part starts to contract, thermal contraction because of losing heat, the continuum of this mercury channel actually breaks over here. This is very much similar, like, let's say, try to think about it. If you have a bit of a liquid flowing over here, and if you slowly start to reduce the availability, if you slowly start to cut it off, if you have a very thin space over here, there exists a certain point where the liquids are going to detach from each other, because now this part is not losing heat. You have to understand this part. This part is still pretty much maintaining, let me use red. This part of the mercury is still maintaining the temperature of the patient, theta of patient. Whereas this temperature, this mercury is starting to go towards the temperature of the room from the temperature of the patient. এই ঘটনাটা কি বোঝা যাচ্ছে কি কি বলতেছে এখানে? No cooling? Yes, cooling. So because the constitution exists over here, the continuum of the mercury breaks over at this constitution, which is a very thin, very thin space, and the mercury of this much space actually returns back into the bulb, whereas this mercury, which is placed on the right side of the constitution, still remains within this space. Thus, the doctor has enough time to get the exact measurement of the temperature. And because there exists a break in the continuum of the mercury after taking one measurement, before the next measurement we always have to shake it, so that all of this mercury which used to be over here ultimately gets back to the bulb, and all the mercury is staying over here, so that we can restart the whole measurement process for a new patient or for the same patient one more time if we want to do it a second time. That's why the shaking is required. Any questions so far?
Sir,
হ্যাঁ বলো।
due to the constriction, the rate at which the mercury expands is the same as the rate at which the mercury contracts?
Well, mercury actually does not expand in the constriction. You have to understand the constriction is a part of the whole passage, which is extremely thin, has the capability to break the continuum. The mercury expansion practically happens in the bulb. The bulb receives the heat from the patient's body, and because mercury is a good conductor of heat, being metal, the rest of the mercury which is over here, they receive the temperature or the heat energy by means of conduction of heat through the metal. These mercury which enters into the bore do not receive the temperature through the glass wall at all, because this glass wall is pretty thick. They receive the temperature or they receive the heat from this location through conduction process in metal. So expansion does not happen in the constriction. Expansion happens inside the bulb. Mercury can push through the constriction when the expansion is happening, but whenever it is pulled back, the mercury continuum breaks at the constriction point. That's how we define the thickness of the constriction, so that it can be disconnected. Does it answer your question?
No, my question was the rate at which the liquid expands. Is it the same as the rate the liquid contracts due to the constriction?
Yeah, definitely. Because if that did not happen, how would we have delta L proportional to delta theta? If this is a straight line, the amount of increase of length that you're going to get over here for the same temperature, if the temperature drops by the same amount, it has to come back by the same height, which means if delta L is same, which means also what? Delta V is also same. So volume expansion rate and volume contraction rate per degree Celsius has to be same. That's the whole point of a linear line.
Got it, sir.
Beautiful. Nuran, you raised your hand. Go ahead.
Sir, why is the bore rectangular?
Oh, the bore is usually designed to be rectangular. Well, here's the thing. We need to have a very thin bore to have a very high sensitivity. And also having a thin bore reduces the requirement of mercury. Mercury is not very cheap. You have to understand. Mercury is not cheap. So if you make a very thick bore, then you have to use more mercury within the thermometer. So we want the bore as thin as possible, so that we have to give less mercury in every thermometer. But we also want the doctor, be able to read off that mercury level conveniently. So that's why we keep it in a rectangular shape, so that the thickness is maintained to be pretty thin, whereas this entire surface works as reflector of light, because mercury is a liquid metal, which means it gives a very shiny surface, pretty much like a mirror. So whenever light rays comes in, let's say light rays actually converges up, and eventually whenever it's reflects back to the patient, to the doctor's eye, that person sees a very bright and wide reflection of the whole thing, so that it's easier to read off against the calibrated scale. Does it make sense?
Yes, sir. Thank you.
No problem. Anything else about this chapter? বলবান তোমরা বইয়ের থার্মোমিটার চ্যাপ্টারটা জাস্ট বইয়ের যে চ্যাপ্টারটুকু আছে তোমরা যারা বই থেকে পড়ছো, for those who have read the Federal book for this temperature chapter, if you have any question you ask me. For those who haven't read the chapter, go to the first page of this chapter, slowly skim through pages and see if you have any question. And for those
Sir,
who have already read, you can ask me the question. বলো।
sir, do we need ওইসব থাকে না differences between the mercury in glass thermometer and alcohol in glass thermometer?
Yes, you need those.
Okay, sir.
The tables are always needed, and eventually eventually whether you're going to appear for your actual practical exam paper 3 or your alternative practical paper 4, no matter which of these papers you appear for, you need to have a good grasp on the experiments that is described in your book. It's pretty important. In every chapter you're going to find out there are certain experiments which are usually printed in blue if you have one of those books, sky blue color, and you need to read through those experiments. It's not essential that you have to memorize those. You have to remember every itsy detail of those experiments. What is important that you understand how the experiment was performed, what is the physics behind the experiment, and how the measurements were taken. I'm saying three things: how this experiment was performed, I mean, what are the steps of this experiment, how, what is the physics behind it, so what is the underlying principle, what is the equation, what is the theory that govern this experiment, and also how the measurements were taken. I mean, if you're using a meter rule, how you're taking the meter rule reading. If you're using a stopwatch, at which point you are pressing the stopwatch on, at which point you are pressing the stopwatch off. So sorts of things like those. So these are the three things that you need to make sense for every single experiment if you read through. If in any of the book experiment, if it doesn't make sense to you, if you have difficulties, you can always ask those questions in the class. Always. It's important that you understand those experiments. বুঝছো কি বলছি?
Yes, sir.
Okay. So বই থেকে যদি আমাদের কোনো কোশ্চেন না থাকে, I'm gonna try to help you with the paper 2 MCQ, paper 2 over here. Give me a bit of a time. দাঁড়াও, আমি তোমাদেরকে একটা কোশ্চেন বের করে দেই, তারপর তোমাদেরকে P2টা আমি দিতেছি। আর এটার প্রিন্ট আউট শুরু হয়েছে, সো আমি খুব শীঘ্রই তোমাদেরকে দিয়ে দিতে পারবো। আর হচ্ছে নোটগুলো আমার গুছানো প্রায় শেষ, সো ডোন্ট ওয়ারি। So this is question number 1. এইটুক করা শুরু করো। Everyone else? এটা বুঝে গেছে?
জি স্যার।
আচ্ছা, কারো কোশ্চেন থাকলে আমরা বলো, I'll help. এরপর আছে সেখানে একটা থার্মোকাপল থার্মোমিটার রাখতে হবে। I'll let you try to achieve this on your own. So তুমি যদি কপিতে আঁকো তাহলে তোমার একটা কষ্ট করে তোমাদের পুরো বানসার বানা আঁকা লাগবে না। কপিতে যদি এখন অ্যাটেম্প করো, just draw a flame, which the drawing the flame is pretty simple, and then you go ahead and try to draw the remaining setup and try to write these answers. Whenever you are writing descriptive answers, kids, listen to this very carefully, although I've said this many times and I might as well be saying this many times in the upcoming future. Whenever you're writing descriptive answers, take a very good look at the marks that you're writing for. Always prefer to write at least one extra point compared to the marks that you have. If it's a 2-mark question, try to write at least 3 individually different mark scoring points. If you wonder why do I need one more, because you don't know what the mark scheme has when you are actually applying the O-levels exam. If you write at least one more extra point, you might actually get both the points within your answer. But if you write exactly 2, there is a possibility that one of your answers, one of your answers or one of your information might actually exactly match with the mark scheme. The other information might not match. It's not, I'm not saying that your other information is wrong, but maybe the examiner thought something else of that question is more important than what you thought was more important. So writing at least one extra point always keeps both ends meet. বুঝছো কি বলছি?
জি স্যার।
ঠিক আছে, at least একটা পয়েন্ট বেশি লিখবা, and I really appreciate that. And try to make a practice of this for the whole series thingy. It's a bit more effort, you learn more, and you are on the safe side. কারণ মানে সত্যি কথা হচ্ছে কি যে 89% পেয়ে A স্টার মিস করা বা 79% পেয়ে A মিস করার মতো কষ্ট পৃথিবীতে খুব কম আছে। So every mark matters. তোমাদেরকে থার্মোমিটারের অ্যাডভান্টেজ পড়াই নাই, পড়াই নাই।
না স্যার এখনো পড়ার নাই।
হায় হায়, এটা তো ভুলে গেছিলাম। আচ্ছা দাঁড়ান, নোটটা বাই করি, তারপর পড়াইতেছি। বিলকুল ভুলে গেছি, বিলকুল। এখানে নাই, এখানে নাই, তার মানে আমাকে খুঁজে বের করতে হবে এটা কোথায় আছে। ওকে, এক মিনিট, আমি থার্মোমিটারের অ্যাডভান্টেজ ডিসঅ্যাডভান্টেজ গুলো একটু তোমাদেরকে পড়াই দিই, তাহলে এই কোশ্চেনটা দেখে তোমাদের জন্য ইজিয়ার হবে। গিভ মি আ বিট অফ এ টাইম, let me just try to find out the thing. সব হলো থার্মোমিটার লিখতে চলে আসার কথা। থার্মো, all right. This is a thermometer, and here we don't have the advantages. Why? এই তো পাওয়া গেছে। বলবান এই পানগুলো একটু পড়ো, have a read at it. সবগুলা পয়েন্টই পড়ো, তারপর আমি যেটা যেটা বুঝছো না সেটা বুঝাবো।
স্যার আপনার চ্যানেল থেকে নয়েজ হচ্ছে, বিপ
হ্যাঁ,
বিপ।
আমার পিসির পিছনের কুলিং ফ্যান, এটার বেয়ারিং ক্ষয়ে গেছে, একটু বড় 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 করে। আচ্ছা, বিয়ারিং ক্ষয়ে গেছে কে, এই কথাটা মানে বুঝছো কে?
স্যার
It's a very, what can I say, very Bangla expression. In English it means it worn out, it's worn out. আচ্ছা, 3 নম্বর পয়েন্টটা জিজ্ঞেস করছো নুরেন, so yeah, I'll go for it. Have a look. It says it can measure distant temperature. Distant temperature means that, what do you understand, that in a thermometer we have a cold junction and we have a hot junction, and we can place the voltmeter anywhere within those two wires, anywhere. So it is possible that we can stand close to the cold junction and attach the voltmeter close to the cold junction and take a long pair of wires which are not touching each other. So we can use some insulation and eventually expose the two wires out of the insulation close to the object that we want to measure the temperature. For example, let's say it can be a furnace, it can be a cooking pot, it can be a steel manufacturing plant, it can be inside the inside of a radioactivity reactor. So you can place the hot junction exactly at that location, and you can be pretty far away observing the voltmeter close to the cold junction. That's achievable. So that's what we mean by saying that you can measure distant temperature, which is not possible if you are trying to use liquid in glass thermometer. If you want to use a liquid in glass thermometer to measure temperature, you have to be present at that location. But for thermal thermometers, that's not necessary. That's not necessary. You can be pretty far away and still be able to measure the temperature of a really far away object precisely. বুঝতে পারছি?
Ji, sir.
Beautiful. So number 4 is just very high responsiveness. You might wonder that why does it have very high responsiveness? Why does it have a very high responsiveness? I'll tell you why. What is the whole point of responsiveness? Responsiveness is about how much time does the thermometer requires to give us the stable temperature reading. Give us the stable temperature reading. So you have to place the thermometer in contact with the unknown temperature object. Let's say a hot object. Hot takes less time to say. So let's say you're gonna place the thermometer in contact with the hot object, and you need to have a stable reading on your device, stationary reading, and that's your final temperature. For the thermal thermometer, the size of the hot junction can be designed to be extremely small. It can be as small as a tip of the nail. You can make it that small. And also metals are good conductors of it, which means the amount of material which needs to be heated up to the temperature of the object is small. So the required heat is pretty small. Also, the object itself is also a good conductor of it, which means together these factors can add up to a very small time required to reach the temperature of the hot object. A small mass requiring small heat and also being metal, the heat transfer rate is very high. Together these two factors can add up to a really small reaction time. এই লজিক থেকে বোঝা যাচ্ছে? বলবান Did I mute myself?
No, sir, we can hear you.
এই কথাটা কি বুঝছো?
জি স্যার,
হাই রেসপন্সিভনেস কেন হচ্ছে? কারো কোনো কনফিউশন?
No, sir.
Beautiful. One of the examples that I can tell you that it has a very high responsiveness, I can tell you one of the examples I can tell you is that let's say you are trying to feed milkshake to a 3-year-old. It cannot eat too much milkshake, but let's say so you give it a small milkshake, and milkshakes are liquid, so they are very easy. They're actually the most efficient form of food intake. So it's not going to take much time. Something like that. Any other problem among the other points? The very last point is says that the only disadvantage is that it is a costly equipment. So the initial buying cost is significantly higher compared to a alcohol thermometer or a mercury thermometer. And there's another problem is that to run the digital voltmeter, if you are using a digital voltmeter, you have to use batteries, which means not only this is a costly equipment to begin with, to operate this thermal thermometer effectively over the duration of its life, you have to replenish batteries. You have to buy batteries. So it has a continuous running cost as well, which is not the case for alcohol thermometer or mercury thermometer. You buy them once, that's it. As long as you don't break it, you can use it for the rest of your life and even more so. So that's the only disadvantage, but it has all the advantages that you can think a thermometer is capable to have. It is very, very sensitive. It has a very high range. It can measure distant temperature. It can measure localized temperature. It has a very high responsiveness. So every good thing that you can think of for a thermometer, thermal thermometers provide us that. ঠিক আছে?
স্যার,
Yes.
স্যার এটার কি কোনো ম্যাক্সিমাম টেম্পারেচার আছে যেটা এটা মেজার করতে পারবে?
Yes, typically the two metals that we use for the two where one of the metal has a higher melting point, the other one has a lower melting point. Typically, thermocouple thermometers can measure the temperature properly up to the melting point of any of those two metals. So as long as the metal is not melting, it can actually measure the temperature pretty precisely, typically. So if you choose materials with really high melting point, then you can have a really high range.
Sir,
Yes,
ক্লাস কি শেষ করবেন?
আর টু পর
স্যার আরেকটা কোয়েশ্চেন।
বলো।
সো স্যার এরকম কি কোনো কেস থাকতে পারে যেখানে দ্য টেম্পারেচার ইজ সো হাই দ্যাট উই ক্যানট মেজার ইট উইথ দি থার্মোকাপল?
Yes, yes, definitely. Sun,
তখন কি দিয়ে মেজার করি স্যার তাহলে?
pyrometer.
ওকে।
Have you guys ever seen the action of a pyrometer?
নো স্যার।
No, sir.
দেখাই। I'll pause the recording because I'm going to show you some YouTube videos, copyright issues. So I pause the recording. I didn't. In those shades of fairness, you have dark and bright, and so on and so forth. So you can actually label those, let's say, level 1 fair, level 2 fair, level 3 fair, or you can say -1 fair, -2 fair, something like that. If you start from 0 at the middle and you can go up and down. So that's a way to compare different skin color, not undermining any skin color person. That's just a way to compare skin color. We can all have different skin depending on the melanin in our skin. The point is that once you have a standardized scale printed paper, you can actually graduate the total human population based upon that color. So once you have a definitive scale, you can use it to go for doing other stuffs. The way parameter works is that we have, let's say we have a hot object that is maintained at a certain temperature, and any hot object will radiate infrared radiation out of it. And using some other thermometer, maybe a thermocouple thermometer, maybe a liquid and glass thermometer, we are going to measure the exact temperature of this hot object manually. And then we're going to place a pyrometer, which basically measures the amount of infrared radiation in terms of intensity at a certain distance. Let's say we're going to keep that pyrometer exactly 1 meter away. And we're going to measure how much infrared radiation does it get. We're going to define that amount of infrared radiation to the temperature that the other thermometer measures. So let's say the thermocouple thermometer measures, let's say the temperature of the hot object is, let's say, 500 degrees Celsius. And we're going to place the pyrothermometer aiming at the hot object at 1 meter distance. And we're going to measure precisely how much infrared radiation this pyrothermometer is receiving. We're going to attach that value of radiation to 500 degrees Celsius. That's one of your scale value. Then you can increase the temperature of the hot object. Let's say you increase it to 700 degrees Celsius, you get another value for the pyrometer. So you now have two values. Depending upon these two values, you can graduate the scale. So the idea is, if this parameter now is held at about, or to be exact, at precisely 1 meter away from a hot object, by measuring the amount of infrared radiation it is giving out, it can convert that infrared radiation amount into relevant temperature scale, because it has the algorithm and the set values within itself. So you can do the math digitally and show you the temperature reading. Is it not possible? What I'm saying is basically something like this. Let me just show you. It might be better understandable for you. Let's say this is a temperature versus infrared radiation intensity graph, intensity of infrared radiation. Let's say this graph looks like this. So let's say you, by experiment, you fed this value to the thermometer. By experiment, you fed this value to the thermometer, and you told the thermometer that the whole graph is linear. So whenever the thermometer measures this much infrared radiation, you can very well tell you this is the temperature. If it measures this much infrared radiation, it will tell you this is the temperature. That is possible, right? That's what I'm saying.
Yes.
That's basically how a parameter works. So what we did, we did not actually reach up to the sun to measure the temperature of the sun. What we did, that we on Earth, with effort and with repetition, we created very precise, very reliable pyrothermometer, which can give us very precise reading depending upon the distance. Then we use those parameters to measure the radiation from the sun. And those readings for the radiation of the sun were taken over the whole year. because our Earth is not at the same distance from the sun for every single of our year position. The shape of the shape of the orbit of Earth is not essentially fully circle. It's a bit elliptical. So sometimes you're pretty far away, sometimes you're pretty close. So the point is, by achieving all those values and averaging it out, we can have within acceptable range of error, we can estimate quite accurately what is the temperature of the sun by measuring the radiation amount. Does that anyhow make sense?
Yes, sir.
Okay. We can actually pause today's class for the time being. There are only 5 questions in the paper 2 question. We already solved one, and I showed you the solution for thermocouple question in one of your earlier class. So practically you are left with only 3 questions. If you can manage time, if you can manage time before tomorrow's class, you can attend those questions. I would really appreciate that. If you can, if you can't, no big deal. We're gonna see the solution of those class questions in the next class, and also in our next class, we're gonna start the next chapter, which is the heat capacity. Heat capacity is a very mathematical chapter, so I highly request none of you to miss classes. Even if you do miss classes, please try to see the YouTube lecture before the next class. That's important. আজকের মতো খোদা হাফেজ, thanks for the late class and good night. Assalamu alaikum.
Assalamualaikum, sir.
Bye, sir.
Bye.